Okay, let's get started here. Okay, so as I always say, turn on your cameras as much as you can. Okay, I don't need to see, it may not be necessary for me to see everybody in the class, which I probably can't even see you all, but I can see like half the class, and that'll be good because, well, it helps me, um, get a better sense for where students are. Okay, so let's start. Are there any questions from what we covered in the last lecture?
Oh, sorry. I just had a question about the difference between CNF and DNF.
CNF and what?
And disjunctive normal form.
Yeah, disjunctive, yes.
Yeah, so like one of them is like and on the outside and or on the inside, and the other one's the opposite. Is that like how it works?
Right. Disjunctive normal form means the top level symbol is a disjunction, right? The outermost symbol is the disjunction. Conjunctive normal form means the outermost symbol is a conjunction.
Thank you.
Anything else?
I have a question.
Yeah.
So I was wondering, will we be eventually receiving like a reference table for all like conversions from like and into or and all the different like logic properties? Like
There aren't that many to, worry about, right?
okay.
So it's the implication that for implication you should remember, and I don't think anything else is really so important or difficult to derive that. So I don't really remember anything else.
Okay.
I
I was just wondering
will.
like I was just wondering when I was like trying to like start the homework, I was just kind of confused on like how would I know when like for example P and Q, how would I know what that is equivalent to? Like besides using like truth tables for each and every like individual logic, I don't know what to call it.
Well, so naturally I expect you to have some intuition for what the formulas mean, right? To some extent. Right? So because we all, use conjunctions and disjunctions in English, so certainly we have some idea, and that helps.
Okay.
Other than that, I think, sometimes if I say show that two things are equivalent, then you might use a truth table, or you might use some identities that say certain things are equivalent to certain other things. And the number of such identities that you have to remember, I'm not able to say now, what are those identities that you should remember. Obviously, De Morgan's laws are something that I expect you to, know, right? So there will be a few things that we will come across that you should remember, but it's not a lot of things to memorize, right? So this is not a memorization course.
Okay. Will we go over more De Morgan's? I feel like we kind of like went over it quickly, but I didn't really have that much time to absorb it.
Yeah, I think De Morgan is something that all of you know from high school, right? So it's just appearing in a different form, and it's really not that different.
Okay.
Okay, so a little bit of the familiarity comes from doing the problems, right? So what I will do is that I will, if, as you start doing the homework, you're still having trouble, say next Tuesday, then we will revisit that, right? And then again, you have a recitation this afternoon, and that's another time to sort of bring up the question, and you'll have the TAs answering your questions there. And that can help sometimes because number one, you're in a smaller class, so it's easier to speak up. Secondly, TAs are generally less intimidating than professors. So, and thirdly, they will explain things in a somewhat different way from the way I do. And simply hearing things explained in two different ways will hopefully help you understand things better. Right? So again, sometimes it's better to just try to do the problems and then revisit if things are not clear yet. Okay? Anything else? Any other questions?
This is a more general question.
Yeah.
But maybe we still have to get to this. But how exactly does what we're doing right now? What's the relevance of it? Like, where does it fit in?
Where does it fit in? So
Yeah.
this is your first course, right?
Right.
So, so essentially, right? So you have to know some of the basics in order to understand the vocabulary of computer science,
Okay.
right? So we are trying to pick up this vocabulary of computer science, right? How do we say things precisely? Because if you can't describe your problem precisely, then neither you nor somebody else can solve this problem, right?
Okay.
So if you want someone to write a program, well, if you can't tell them precisely what it is that you want.
Mm-hmm.
So what we are learning here is how do we, at least at the moment, right? So in the first few lectures, we are trying to understand how, things that we say in English can be made more precise and formal.
Okay.
Okay.
Yep. Thank you.
Okay, very good. Those were all very good questions. And again, some of these questions I can't answer very well, such as the one that was raised just now, because again, as you go through the course, you will, realize, how it's giving you, I guess it's like, when you learn the alphabet, it may not be entirely obvious to you how this is, going to connect to, writing poetry that you might write in sort of, many years down the line. So it's a little bit like that. So we are in very early stages, and to some extent, I'll try to explain where things are useful. To some extent, you just have to believe us and stay with us, and with some time, and especially towards the later parts of this course, and most certainly as you go into some of the future courses, you will see how different things connect together. Okay. Very good. Okay, so the other thing that I do want to say is that part of what we are trying to do in this course is to convey the excitement of computer science, right? So what is interesting, what is fascinating, what will keep us going for a very long time, right? Because computer science is a discipline where you need to learn constantly, right? So it's not something that you get your degree and then you're done, right? So if you are someone who doesn't enjoy learning, who doesn't enjoy doing new things, who doesn't enjoy interesting things, then you will find soon enough that the profession is not a particularly suitable one for you, because it requires, it is surely very rewarding in terms of posing intellectual challenges and making you deal with new things all the time. At the same time, if that type of at the same time, it requires you to be on your toes and learning new things all the time, right? So if that's not your thing, then you are either going to run out of steam or simply find that it's just not the profession for you, right? So what I'm trying to do and what we try to do in this course is to try to make the profession, make computer science interesting to you. So, when you take up a job or do other things in your future, you're not saying, hey, why should I do this? What is the benefit I gain? Rather, you say, hey, this is fun. I'm doing this because it's fun. I wouldn't do anything else in my life. So that's, it's much easier to sustain yourself for the long term, right? So all of us have professional careers that are, that you can expect to be like 50 years, right? And if you are not excited, if you don't think it's fun, then it's going to be much harder to keep going after the first, say, 5 years, right? So our goal clearly is to try to convince you that this is actually fun, okay? How much we succeed, we will know, but that's part of the goal, right? So to some extent, yes, we want to do things that are relevant, but sometimes we are just, going to say, hey, this is just interesting and fun, and that's why you do these things. And of course, not everything that I'm saying is so not everything I'm saying is going to be interesting for everybody, but my hope is that some of it will be interesting to some of you, right? So that you will find, your area, your niche, the things that really interest you, and then build on that, right? So again, we are trying to give you sort of a broad background, and hopefully some of the things I say will tickle your interest, and you'll pick up from there. Okay, so coming back from, resuming from where we were last time, excuse me. So we were talking about normal forms and the satisfiability problem. And I was trying to say that the satisfiability problem is difficult to solve in the conjunctive normal form, but it is quite easy to solve in the disjunctive normal form, because in the disjunctive normal form, you have a disjunction of conjunctions, right? And you just have to pick one conjunction and make it true. And you know how to make a conjunction true. You make every positive literal in the conjunction true and every negative literal false. So for instance, if you take something like this, then you'll make P1 true, P2 false, and P3 true. And then this whole conjunction is now going to be true, right? Because now every literal there is true, and therefore its whole thing is going to be true. So now if you have a disjunction of conjunctions like this, then you can simply pick one of the conjunctions to make true, and you can very quickly say, here is a truth assignment, that is an assignment of true or false to each proposition, right? And you can say, okay, by setting this proposition to true, P2 to false, and P3 to true, I can make this whole thing true, okay? But that's not the case if you have a conjunctive normal form, because in the conjunctive normal form, you have to find a way to make each of them true, right? Only then the whole conjunction will be true. And then if you have, something like P1 or, not P2 or P3, right? You know how to make, one of these to be true. So for instance, by setting P1 to be true, you can make this whole thing to be true. But what if I have this and not P1, right? So if I make P1 to be true, then this will become false. And so the whole thing will become false, right? So with the case of conjunctive normal form, I have to be more careful in picking which propositions are going to be true and which ones are going to be false, right? And that's finding the ones that we want to set to be true and we want the ones that we want to set to false. This is the SAT problem, right? The satisfiability problem, which is one of the hardest problems known in computer science, and a lot of theory about efficient algorithms, right, has been built on the basis of this satisfiability problem, right? So basically, we would often say, hey, this problem is hard because if you can solve this problem, then I know how to solve this satisfiability problem. But we all know that satisfiability, even though people have been working to solve it efficiently for hundreds of years, nobody knows how to do it efficiently. And therefore, this other problem that I'm trying to solve should also be hard, right? So this way, it gives us some structure to the way we approach hard problems. Instead of saying, hey, I'll just try something, right? And failing, you have a way of saying ahead of time, hey, this looks like a hard problem, so I'm going to fail. I'll prove that I'll fail and then move on. Okay, so let's talk about a few more concepts. What are axioms, inference rules, theorems, and proofs? Okay, an axiom is a proposition accepted to be true, right? I mean, an axiom is an English word that you have heard, and whatever it means to you in English is roughly what it means in math too, right? It's a proposition that's accepted to be true. Very often there's no way to prove them, but it seems so obviously true, right? So for instance, we could say, hey, if you have 2 points in space, you can draw a straight line through them, right? So if somebody asks you to prove it, then it's really not clear how would you start, right? Where would you start? What does it even mean to prove it, right? So instead what we do is that we say, okay, hey, some of these things seem self-evident, so let's just assume that they are true and then try to prove other things on the basis of these things, these assumptions, okay? So there are special types of axioms called inference rules, okay? Very often people don't call an inference rule as an axiom, but they are kind of the same in the sense that they are, again, assumed to be true. The main difference is that an inference rule allows you to derive new propositions from existing ones, okay? So here is a very simple and intuitive inference rule that's called modus ponens. And it basically says, if you know P to be true, and if you also know P implies Q, then from that you can conclude that Q is true, right? Because P implies Q says that whenever P is true, Q is true, right? And in addition, you are given the fact that P is true, right? So when you combine P is true, and then if P is true, then Q is true, then you put the two together, then you get the result that Q must be true. Okay, so this is a very simple example of an inference rule. And then what is a theorem? Theorem is something that you can establish by starting from the axioms and repeatedly applying inference rules. Okay, so the idea is that every step in your proof is based on what we have all agreed to be true, right? They're all axioms and inference rules. So just starting from that, you are able to establish some proposition, some formula, then that formula is called a theorem because you have been able to prove its correctness based on your axioms. Okay, so so a formal proof is going to tell you exactly the manner in which a theorem was derived from the axioms. So it's going to say, hey, here is the axiom that you take, and here is the inference rule that you apply, and then by putting this together, you get this intermediate result. Then you take this intermediate result, combine it with more axioms and inference rules, you get another intermediate result, and this goes on and on until you basically get to the formula that represents the theorem. Okay, so let's take a very simple example here, right? So you are given this inference rule, okay, and then let's say you are told that these two are true, okay, then how can you formally prove R? So we write down what we know, right? So we know P implies R, right? So these are given to us, right? So we are told that these are true, okay? Then we are asked, if these two things are true, can you say that R is also true, okay? So given these two as initial conditions or facts, then we try to apply the inference rule, right? So we can apply this inference rule, right, with phi as P and psi as P implies R, right? So you try phi, if you set phi equal to P, then it matches this part. I'm sorry. Okay. So you have P. Okay. Now, so psi is, yeah. Okay. So now you can see, you can match phi is P. So that is this. And phi implies psi. Okay. So that matches again. This is phi. This is phi. This is psi, right? So you can see that very easily that these two given pieces of information match the top of this inference rule, right? So again, the way to read an inference rule is that the preconditions for applying the inference rule are above the line, and what you can conclude based on those preconditions is below the line, right? So we are going to apply the inference rule, and the inference rule, we can derive psi, and we said that psi is nothing but P goes to R. So we can derive P implies R from these two steps, okay? Now we can apply the inference rule again, this time with phi equals P and that being psi, right? So by taking these two and applying the inference rule on those, then we get psi, which is R, right? So we wanted to prove R, and we have proved R, right? So all we needed was, we needed to apply the inference rule twice. And of course, we needed to know, where to apply the inference rule. So we needed to, in the first step, of course, there are only two things. So you needed to choose only one of those two. In the second step, there were three intermediate, two facts and one intermediate result. And then we needed to choose two of them to apply the inference rule, and then we got, the result. Okay. So in general, a formal proof consists of, you start with the information that's given to you, right? The formulas that are known to be true, such as, P and P implies R. And then you repeatedly apply the inference rules until you get to the statement of your theorem. Okay. So this is called a formal proof to, right? Again, I use the word formal proof to say that it's essentially a completely mechanical process, right? So I tell you, here is the rule, here is the axiom, and it's not up to your imagination or insight in order to figure out that each of those steps is correct, but instead you are simply applying the axioms and inference rule in a mechanical fashion, right? So that is why it's called a formal proof. So there is this field of automated theorem proving where you are going to get computers to prove theorems. And these automated theorem provers are essentially constructing these kinds of formal proofs, right? So you give them a bunch of axioms and inference rules, and they kind of figure out, okay, here is a place where I can apply this inference rule. Here is a place I can apply this other inference rules, and so on. And then they try to find a proof of the theorem that you want to prove. Okay. So what is the challenge? The challenge is that typically there are many axioms and inference rules to work with. So at every point in time, the automated prover can choose from many different facts and inference rules, which means that it becomes some kind of a search problem where the computer algorithm has to figure out which inference rule to apply at which point in time, and which intermediate results to which these are going to be applied, and so on. So it becomes very quickly the number of possible combinations increases exponentially, and very quickly you get to a situation where there are just far too many possible ways to go, and the system essentially is not making progress because there is no good way to figure out which path to take, right? So we somehow rely on some kind of intuition and insight, which sometimes help. Computers, the simplest thing that they can do is to use brute force search, right? So they are very fast. They can, we cannot systematically go through more than, our ability to, search through possible approaches is of the range of 1 per second to 1 per few minutes, whereas computers can do this millions to billions of times faster than us, right? But the problem is that the search space, the space of possible inference rules that can be used is the number of combinations is so large that even though the computer is going, can look through many possibilities, it really is, very so very quickly the number of possibilities becomes too large for a computer to make progress, and so this is sort of very a long time ago when people formalized logic using axioms and inference rules and so on. People believed that very quickly complex results can be proved quickly because there is a mechanical way to prove things. But then, people realized, that the space of possible proofs is so large that you're not going to make progress, easily. So, so essentially what has happened is that this area of automated theorem proving remains a very active area of research, an area where people have worked on for, ever since the beginning of modern computers. But it still remains an area where progress has been made only in very limited contexts. And we are just now beginning to see progress in an area called machine checkable proofs, where where humans are still involved in creating the proof, but humans try to make the big decisions, right? So higher level strategies for how to go about doing the proof, and relying on machines to work out the details. And that's what is being done in terms of automated proofs. And then the flip side of that is checking the proof, which is that if somebody developed a proof, again, humans make a lot of mistakes. And so, when something important is being proved, it'll be helpful if there is a way to check the proof. And again, machines can check the proof, because once again, it's an application of axioms and inference rule in a mechanical fashion, and whether the rules are being applied correctly at each step is fairly easy. As I just mentioned, the real problem is figuring out what inference rule to apply at what point, right? So that is where insight is needed, right? So the only difficult thing about formal proofs is figuring out what to do next, right? What inference rule to apply next. The actual application of that inference rule is entirely mechanical, and it can be automated, and it can also be checked by a machine, but machines are still not able to figure out what is the next step. So in this course, of course, we are not going to do anything like formal proofs. Formal proofs tend to be extremely long, and at the end of a very long proof, you would have proved something that seems quite elementary. So we are going to do essentially informal proofs, which is which means that we'll end up relying on numerous results that are known, right? So we declare that there are lots of things that we know. Pretty much everything that you learned in high school math, we will assume is known, and then we'll try to see how to prove something based on those results. The results may be inference rules, can be thought of as inference rules, axioms, intermediate theorems, whatever you want to think of them as. But then we will draw on all of those to try to prove our result. Okay, so that is sort of a little bit of a background about the process of formal proofs. Now we transition to talking about informal proofs that I want you to be able to do in this course, right? So again, some of the so in your first homework, half of it is about propositions, which we more or less had covered in the first week. The rest of it is on proofs, and that material, although we introduced proofs in the first lecture, those weren't necessarily the kind of proofs that you will be able to do. So now what we want to do is we want to sort of go through proofs in a more systematic way, so that all of us can write some proofs. Okay, so let's start by taking the very simple case of proving an implication, right? So if P implies Q, right? So like the inference rule that we talked about. So we are going to assume P and then see if with that information we can show that Q is true. Okay, so let's start with this example, right? So if 2 less than x less than 4, then we want to prove x squared minus 6x plus 8 is less than 0. So does anybody have an idea how we might proceed?
We could factor the right hand side.
Okay, so again, there is no, nobody can immediately say, okay, here is the right way to do it, right? So when we try to prove things, we try approach 1 and approach 2 and approach 3 and so on, right? And then we hit upon, somewhere along the way, we hit upon the right approach and then we are able to prove, right? So the first suggestion being given is factorization, right? So let's factorize the right-hand side. Okay, so this is P, this is Q, right? So let's express Q in a factorized form, right? So what is that? Can someone tell me how to factorize it?
X minus 2 times x minus 4.
So this is x minus 2 times, right? So we can rewrite Q in this form, right? So so you can verify that, okay, minus 2 minus 4 is minus 6, so it matches this coefficient, and minus 2 times minus 4 is plus 8, which matches that, right? So we know that this is a correct factorization of x squared minus 6x plus 8, right? So so let's assume that P is true, right? Which means that P says that x is greater than 2, right? And x is less than 4, right? So let's assume P, right? And then try to reason about the sign of Q, right? Is it positive or negative, assuming P is true, right? So if x is greater than 2, okay, so that means this is going to be positive, right? So assuming P, x greater than 2, right, says this is positive, and x less than 4 says x minus 4 is going to be negative, right? Again, keep in mind that when we write proofs, anybody can make mistakes, and I'm sure I'll make a few mistakes in my proofs, in the things that I'm trying to prove. So don't be convinced that, don't hesitate to speak up if you think there is something wrong. Okay, chances are that you picked up on a mistake that I made. Okay, so now we have a product of two numbers. One is positive, one is negative, right? Therefore, this whole product should be negative, right? So we started with assuming that P is true, and once we assume that P is true, now we are able to prove that Q is true. That is, this expression is actually negative, right? So that's how we prove an implication, right? But of course, the exact manner in which P helps you prove Q is going to differ in different problems, right? So in this problem, it was, well, you needed to do this factorization and reasoning about the sign of each of those factors in order to go from P to Q. And there may be other problems where you might have to use a different strategy. Any questions?
I have a question.
Yeah.
So what did you write under x minus 2? I can't really make it out. It was like, is that say true? Or
It's positive.
positive, and then what's
plus VE.
what
That's
is
what it
VE?
says. Yeah, that's my V, right? V. Okay.
Wait, what does VE stand for though?
So in math, I'm sure you have seen this, right?
Oh,
The shorthand for positive is plus VE, and shorthand for negative is minus VE, right?
okay.
Yeah.
Okay, thank you.
Yeah. Okay. Anything else? Any other questions? Okay. So a second way of proving an implication is proving the contrapositive, right? Remember that we said before, and again, this is something that you have studied in high school. So P implies Q is equivalent to saying not Q implies not P, right? And this is called the right-hand side here. So this is called a contrapositive. Of the left-hand side, right? So it's a contrapositive of P implies Q. So now, because the two are equivalent, you may find that it's easier to prove this instead of this one directly. Okay, so let's take an example. If R is irrational, right? So R is irrational is our P, right? Then square root R is irrational is Q, right? So if you try the strategy from the previous slide, which is you assume P, you assume that R is irrational, and then from that you want to conclude that square root R is irrational, you'll be stuck because there is not a whole lot you can do knowing that R is irrational, right? Because it says that it cannot be expressed as a P by Q with, where P and Q are integers and so on. But the fact that it cannot be expressed, what does it say about its square root, right? It's really difficult to do much. On the other hand, if you go for the contrapositive, then what you are saying is that let's assume not Q, right? So not Q is something like square root 2 right? So the negation of Q simply says that square root R is rational, right? So then we can see that R equals, why can't I write this? Right? That is product of two rational numbers, right? Which is, of course, a rational number, right? Because if this is a rational number, then this can be expressed as, okay, so let's try, right? So this can be expressed in the form A divided by B, where A and B are integers. And this is rational, therefore it can be expressed as a C divided by D, where C and D are integers. So now if you multiply these two, then you get A times C divided by B times D, that is equal to integer divided by integer, which means it's rational, right? So we have shown that R is rational, right? Which is, again, here P is R is irrational. So if we say that R is rational, that means we have proved not P, right? So we started from not Q and have proved not P, right? So we have proved the contrapositive, right? So we have proved this statement, and therefore we have proved the implication. Okay, any questions?
Where'd you get the A times C over B
I'm sorry.
times
So when you say something is a rational number, right? What does that mean? That means it can be expressed as A divided by B, where A and B are integers, right? So that is the definition of a rational number. I'm trying to explain why when you multiply two rational numbers, you get a rational number, right? That's because a rational number is, one integer divided by another integer, right? It can be expressed as a fraction that way. And so if you have A divided by B multiplied by C divided by D, once again, you have this expression where the numerator is a product of integers and therefore it's an integer. The denominator is also a product of integers, therefore it's another integer, right? So it's now again of the form integer divided by integer, which means that the result is rational. Okay, so so in most of these types of proofs, the main issue is figuring out what strategy to use, right? Once you realize that it's a contrapositive that you should try to prove, then the remaining steps become easy, okay? And of course, nothing is going to be easy the first time you see a proof, okay? So this is why we have to see some examples in class, and then we have to try to do some examples on our own, some proofs on our own, and then we need to come back and then say, okay, what are the, what is it that we are able to get and what is it that we are not able to get, and then we can revisit the material that that hasn't hasn't been understood, right? So so now, so far what we did was we talked about two ways of proving an implication, right? The first way was you assume P, and then based on that assumption, you try to show that Q should also be true, right? So that was the first approach. The second approach was to take the contrapositive of the implication you are trying to prove, and then you just prove the contrapositive using the first method, okay? So those are the two methods for proving an implication. Now, if you want to prove if and only if, which means that you are trying to prove something like this, whenever P is true, Q is true, and vice versa, right? And by definition, P double arrow Q is the same as, it's a shorthand for P implies Q, and Q implies P. Okay, so that is what we mean when we say P is equivalent to Q. Okay, so therefore, the way you prove P is equivalent to Q is by first proving P implies Q, and then you prove Q implies P. Okay, so this is not really a new proof technique. It just says, you already know how to prove a two-way implication because it's just twice the work of one-way implication.
I just have like a
Yeah.
general question.
Yes.
So, you know how the title of the slide is proving PIFF? Is
Yeah.
that like, is that like a typo or something, or is that like, so does that mean anything? Just like the double M?
I'm pretty sure it was introduced somewhere before, but if not, IFF is the shorthand for if and only if.
Ooh, okay.
Okay, because mathematicians don't like to, write out a lot of text, and you can see when I write a lot of text, it's easy to make mistakes. So we try to reduce the number of letters we write. So once again, most of what I'm, pretty much everything I'm talking about is in your textbook, right? So you should take a look at the textbook. The reason being that we all learn better by seeing things described in different ways, right? So I'm going to explain something to you in one way, and the textbook might explain it to you in a slightly different way, and then one of them may click when the other doesn't, right? So it's always helpful to look at the textbook. At the same time, you need to sort of make sure that you don't get overwhelmed and lost, right? So if you find that the textbook, you get lost in the way things are said in the textbook, and you don't get as lost in the class, then by all means, you can just stick to the lecture slides. Okay, so it's not that there is going to be material in the textbook that I'm going to quiz you on or ask you to answer in the exam that we didn't cover in the class, right? So the slides will be a superset of everything that I expect you to learn from this course. Okay, of course, it doesn't mean that the slides may not include everything that you have learned in the past, right? So I'm always building on what you have learned in the past in high school. And of course, that material won't be here. But in terms of the new material that we are covering, it's going to be on the slides. If I'm going to expect you to know it, then it'll be on the slide. Okay. Any other questions? Okay, so the next strategy is called proof by cases, right? So you typically have a situation where you say that you once again want to prove P implies Q, right? But then directly assuming P and then trying to prove Q may be difficult. So instead, what you, and typically the reason is that P is somehow a complex condition and it's difficult to work with. And then what you can do is you can break up P into many cases. So you can say when P is true, one of P1 through Pk, right, which are each simpler conditions than P, right? So you can say that one of them must be true, and then you go ahead and say, okay, if P1 is true, then I can prove, Q. And then if P2 is true, then I'll go ahead and prove Q, and so on. So now, basically, instead of starting with a complex condition P, instead you break it down into many cases, and then you prove your result in each case, right? So essentially what you have done is you said, hey, this is too complicated. I'm going to simplify it by breaking it up into a number of simpler problems, right? But of course, now I have, a lot more, things to prove, right? I have to prove P1 implies Q, P2 implies Q, and so on. So I have a lot of things to prove, but each of those proofs is going to be simpler, okay? So let's take an example, right? A very simple example. Max of RS plus min of RS equals R plus S, right? So how would we, can anyone tell me, just based on your intuition, what a proof by cases might look like here?
Well, I think there would be three main cases, like R is greater than S, R is less than S, and R equals S.
Okay, so you can probably, sure, that's fine. So let's take three cases. Okay, so case one, right? Right, and we write so when you do proof by cases, or sometimes it's called case splitting, right? So you split into several cases. One of the conditions is that the cases should, together cover all possibilities, right? So given any R and S, right? So we know that either R must be less than S, or R must be greater than S, or R must be equal to S, right? So when we set out these three conditions, we have covered all the possibilities, right? So that's an important thing in a proof by cases approach. You make sure that the cases are exhaustive, right? So they exhaust all possibilities. Okay, so now let's take case one, R greater than S. Then we can say that max of R comma S equals R, right? Because R is greater than S, right? Therefore, R is going to be the maximum among R and S, right? So we can also say min of R comma S equals S, right? So if you add these two, then you will get R plus S, right? So we added max of R plus max of S, and then you get R plus S, which is the right-hand side we want to prove, right? This is not difficult, right? So again, when you see a problem like this, you may not immediately say, hey, this is a proof by cases, okay? But once somebody says, okay, try these three cases, then you should be able to see the proof, okay? Because then it's not, beyond that, there is no, it's fairly elementary after that, right? But most of the time, the difficulty with proofs is knowing, what strategy to use, okay? And it comes with experience and intuition, right? And until you have experience and intuition, then you will anything that's non-trivial, we will tell you, okay, try this approach, okay? Or we will have done examples in class that are similar, and therefore you will know how to prove something. So for instance, in your homework, one of the problems is show that square root 3 is irrational, right? So we obviously, we did a proof that square root 2 is irrational. in class, right? So what I want you to do is I want you to understand how that proof works and then translate it over to the case of square root 3 instead of, just dealing with square root 2, right? So it's that kind of proof work we will typically expect, at least at this point in the course, right? And later on, we will expect maybe a little bit more, but right now, that's what is going to be expected.
I have a, okay, did you set max R comma S equal to R because R is greater than S?
Right.
Okay, just double checking.
Right. So I presume you can see how the proof would be basically the same here, except that in this case, max will be S. Right. So things are flipped here, but when you add them up, the result is still the same. Right. So you get S plus R equals R plus S. So once again, right. So
Sorry,
yeah. Go on.
I just had a frog in my throat. I didn't realize that my mic was on.
Oh. Yeah, I'm not sure that too many of us noticed. Okay, so and R equal to S is of course very similar. So once again, you'll be able to show that max equals min equals R, and so you'll end up proving that R plus S equals R plus S in this case too, right? So you can work out that case. So many times proof by cases is actually very, very easy to do. If only you know how to break down the cases, then the proof becomes quite easy after that. Okay.
Professor?
Yeah, go on.
Can you go to the previous slide for a second? I wasn't able to copy everything.
You don't have to copy anything, right? Because all of this is going to go on the course web page. Have you saw that, right? You should have seen that from the course web page where the slides are there, the recordings are there, right?
Yeah.
Okay. Just making sure that you're making use of that. Okay. Okay, so that's proof by cases. So now, what happens when the hypothesis is false, right? So once again, in P implies Q, this is called a hypothesis, right? So when hypothesis is false, again, remember P implies Q is the same thing as not P or Q, right? So when the hypothesis is false, then the implication is true, right? So we would say that the implication is vacuously true, right? Because you don't have to do anything. Because P is false, P implies Q happens to be true, right? Even if Q is itself is false, right? So with P implies Q is unconditionally true when P is false. So this is called vacuous truth. And false always implies anything, right? And once again, using this equivalence, false always implies anything. Which means that something that looks kind of silly, such as P implies not P, right? It says that if P is true, then P must be false, right? So those types of nonsensical implications are still valid if P happens to be false, because, well, if P is false, right? So this whole thing becomes true if P is false, regardless of, you know, what the right-hand side evaluates true, right? So whether it is true or false on the right-hand side, it really does not matter. So so if P is false, this is true, right? So now let's take this implication and compute its this is, I don't know what I'm saying here, so just let's ignore that. So what this says is that if you start from P and you can prove that P is, so if starting from P, you can prove not P. Okay, suppose you can do that. That means you have proved P implies not P, right? So you have proved this, but this kind of statement can be true only if P is false, right? So that's the only condition under which P implies not P can be true. Okay, so a proof by contradiction uses this approach. Okay, so you start from P, and if you are able to prove that not P is true, that must be because P itself, your original assumption itself, must be false. Okay, so this is called arriving at a contradiction. That is, you start from P and you prove not P, right? So that is called arriving at a contradiction. Remember, a contradiction is nothing but something that's always false. So P and not P is a contradiction, right? You know. So so if you start from P and then you prove not P, then that's called proving by contradiction. And the net conclusion you can make is that P must have been false to start with. Okay. Once again, as I've told you before, some of you may need a little bit more time to accept that a proof by contradiction is actually a proof. Okay, but that's okay. It'll come with experience, and until you are convinced, you can just take it as a given that if you can prove a contradiction, that means what, you know, the proposition you're starting with is false. So let's try to give another example of proof by contradiction. Okay, so how many of you so how many prime numbers are there? Is there a largest prime number? Of course, it already says there are infinitely many primes. Okay, so so let's write that down slightly differently. That means let's assume that this is false. Okay, so so in a proof by contradiction, what you can do is you can assume P, okay? Then prove not P, right? And then you conclude P must be false. Okay, so this is one way of proving by contradiction. And the second thing you can do, which is actually very, very similar, is you assume you just negate everything on over here, right? So you assume not P, and then you prove P, and then you conclude not P. Okay. No, I'm sorry. Let's write it. This is, if I write it this way, it's a little confusing. Okay. So right? So either you start from P and then you prove not P, and then they'll tell you that P must be false, or you negate everything here, right? So instead of assuming P, you assume not P. Instead of proving not P, you prove P. And instead of concluding that P must be false, you can conclude P must be true, right? So they are all sort of just what you just put a one negation in front of everything here. Okay, so what we are going to do here is something like this. So let me okay, so if there are infinitely many primes, let's assume so let's call this P. Okay, so assume not P, which says right. So the negation of infinitely many primes is that there are only finitely many primes, right? Okay, so if there are only finitely many primes, okay, then call them right. So if there are only finitely many primes, right, let's say there are k primes, let's list them all, right? So we'll call them n1, n2, n3 up to nk, right? So now what we are going to do is we are going to construct this number n equals okay. So we take the product of all these primes, right, and then add 1 to it. Okay, so the claim is that this n, which is the product of these finitely many primes plus 1, right, is a prime number by itself. Okay, why? Because what's the definition of a prime number?
Its only factors are one and itself.
So what is the definition of a composite number?
It has at least one factor besides itself and 1
And this factor should be?
prime.
Yeah, right. So a composite number is one that has at least one prime factor, right? So now if you look at n1 times n2 times, so there are, so if you look for common factors between n and any of these prime numbers, right? There is no common factor, because if you take the prime number n1 divides this product, right? So if you divide n by n1, you're going to have a remainder of 1, right? So as an example, let's take the simple example where okay, so let's take a simple example where, n1 equal to 2, n2 equal to 3, okay? And let's say k equal to 2, so there are only 2 prime numbers that we are working with. So the capital number, capital N, would be 2 times 3 plus 1, which is 7, right? So you can see that if I take 7 and I divide by the first prime number 2, right? I get a remainder of 1, right? You can do it in your head and you'll see that there's a remainder of 1. I take 3 and then again do the math. I try to divide 7 by 3. Once again, I am left with a remainder of 1, right? Which means that, n is not a product of any of these numbers, right? So n is not a multiple of any of n1, n2, n3 up to nk, right? Which means that n does not have any prime divisors, okay? Which means that n itself must be prime, right? Because we said a composite number is one that has at least one prime factor, right? And we have shown that this capital N that we have constructed does not have any prime factors, and therefore n must be prime, okay? So right? So now we have a contradiction because we thought nk was the largest prime, but we have clearly constructed an even larger number, capital N, and we have shown that the capital N is a prime. So we have a contradiction, right? We started with the assumption that there is a largest prime, nk, and then we were able to construct an even larger prime, okay? So therefore, our assumption that there is a largest prime must be wrong, okay? So that means there is no such thing as a largest prime, which means that, anytime you're given one prime, you can always find another prime that's larger, right? Which basically says that, there are infinitely many primes, right? Because anytime somebody gives you a prime, you can say, hey, there is this other number that's larger than this prime, that's also a prime. And then you take that and then you can add on one more to it. And then you can keep doing this and this will never stop. and therefore it must be the case that there are infinitely many primes. Okay, so let's stop here. You have your recitations with the TAs today. I'll be here for some more time. So if any of you are having trouble, you can connect back into this session and then tell me that you're having trouble, and then we'll figure out how to resolve it. Okay? Anything else? If you have any questions, you can go ahead and ask, and then the TAs hopefully told you exactly what time to join the recitation. It's probably like 10 minutes. Yeah.
I had a question about, so you said that the SAT problem with the CNF form was NP complete or NP hard?
Yeah.
But solving DNF by itself was relatively simple, or?
Yeah, it's trivial.
Okay. Then in that case, is converting between DNF and CNF also NP hard?
Correct.
Okay.
It's a very good question. Yes. Otherwise, we'll have some shortcut, right? Yes. So essentially, if you, it's worse than that because it's one of those problems that is known to have a known exponential bound. That is, there exist formulas in conjunctive normal form where if you convert it into disjunctive normal form, the formula will be exponentially larger than what you started with.
Okay.
Okay. So since the formula itself is so large, constructing it is going to take a long time, right? It's not about efficiently constructing, because what you are going to end up with is going to be huge.
Right.
Any other questions? Okay, very good. So yeah, so again, feel free to hang up and join your recitation sessions. And then if you have any trouble, come back.